Today we're going to talk a little bit more about redox reactions. Redox reactions are very, very, very important. All combustion reactions are redox reactions. All single displacement reactions are redox reactions. The one that is not is double displacement, never redox. And acid bases, which is a type of double displacement, never redox. So they're easy to spot. But you're gonna have energy being liberated mostly, right? In this is one that I love because we see it every day, and it may actually change what you want to do for a living. Materials engineering is becoming a hot topic right now because of Tesla and others who are trying to create better, improved materials to do things that they have never done before. And you can literally, just like in chemistry, predict how a material is going to work over a range of conditions. It's crazy, crazy, if you happen to like that. And there are not that many materials engineering. There are not that many. And this one is corrosion engineer. Can you believe there is such thing as corrosion engineer? That's all they do. Why? Because the world is built on steel. A lot of the structures we have in the world are built with steel, right? And that steel will tend to corrode at some point, and we need to do things to it and take care of it and figure out, like a research, what cracked, what failed, why did something fail, why? So if you're interested, and if you like this topic, this may be something you want to go into. Now, in here we had iron, which is a part of carbon steel, right? You had iron as a solid. As a part of the steel that was going to corrode is the iron. And then you're going to have oxygen in the atmosphere. And you're making iron trioxide. How do I write iron trioxide? Iron trioxide, right? The original charge for this was 0. It was iron as a metal. The original charge of this was 0. Was that a stable or unstable thing? Metals and not metals. Do they like to be where they are, or do they prefer to be ions? They do. They prefer to be ions. So, yeah, that's fairly unstable. All the metals want to be combined. Unstable, that wants to rub, and they prefer to be ions. Here, this is happy. That's more stable. Iron trioxide, they are combined. They are one took the electrons from the other, and they have noble gas configuration. However, it does have the typical, and that's another reason I like this, it has the typical ionic salt properties. Ionic salts are usually brittle, right? That's brittle. All of a sudden you have a ceramic on your pipe. You don't want a pipe made with ceramics. You have a ceramic on your pipe that literally is brittle and falls apart. The only thing that corrodes is iron. Copper does not. It does get an oxide layer on it, but it's actually a protective layer. And other metals, the only one that will do this to this extent is iron, but it's everywhere. Carbon steel is everywhere. So the iron went from a charge of 0, well, this is -2, so that's -6, and the iron is +3. The compound is very stable, and it has a 0 charge, but the individual components are going to be, or the individual elements are going to have their own charges, right? The iron got oxidized, and the oxygen got reduced. If you look at the periodic table, I want you to picture this, and we're going to do this next class. We're going to take the periodic tables and update them. Some people wrote more than others. We need to make sure we have in those everything we know. And we're also going to, next class, we're going to work a little bit more with our models, and we're going to update them as well. I'll ask you to buy index cards, or I'll just have paper, but index cards will be better in order to update our models. But I want you to look at the periodic table. Everything to the right of that staircase are non-metals, right? And they all tend to behave like oxygen. So they all tend to be what, Colleen? Reduced. I meant between reduction and oxidation. They all tend to be reduced. So when you look at the right side of the periodic table, we're going to put an add, or somehow we're going to know that all those tend to be reduced. And the confusing part is that they're going to be called oxidizing agents. What's an oxidizing agent? Something that causes something to get reduced. To get oxidized, right? So it's an oxidizing agent because oxygen causes metals to get oxidized. So they're agents that force the other to get oxidized. Why? Because they rob the electrons. And when you rob the electrons, the other one gets oxidized. So this is gonna play with your brains, and you're not gonna like it too much at some point, because you're gonna be, what? Just think oxygen gets reduced, but it's an oxidizing agent, and everybody like him or like it is going to want to do the same thing. Now metals, on the other hand, tend to get oxidized, right? They tend to lose electrons. That's what they want to do. That's how they are more stable, right? Metals tend to lose electrons and they get oxidized, but they're called reducing agents. Because as they get oxidized, they're called reducing agents. Most of the time, I don't hear people talking about reducing agents. I hear more people talk about oxidizing agents, although they're backwards.
So oxidizing agents are non-
Get reduced. Oxidizing agents get reduced themselves, and usually they are non-metals, just like oxygen. Everything on that side, they all want electrons, right? They get reduced. Oxidizing agents like oxygen robs electrons, and that makes it to be more negative, and more negative is reduced. So do you see how this plays with your brain? If you think about it, you're like, okay, I'm gaining electrons, but I'm getting reduced, and at the same time I'm an oxidizing agent, right? This is all, I'm telling you, it is going to play. Maybe you see me now talking about it, it makes sense, but then you're gonna go, what? So I like to keep it as oxygen, and the reason they're called oxidizing agents is because of oxygen. It's a non-metal, it likes to rob electrons, and it itself gets reduced. It goes from oxygen 0 to -2. That got reduced, right? Metals get oxidized, and they are called reducing agents, and they are all the ones on the other side of the staircase. So those are your, those all get oxidized. Two metals is not always the case, because sometimes one metal and another metal, they both have different voltage. Between the two of them, there is a different voltage, and sometimes one metal will oxidize the other. The one that wants to get rid of the electrons the most will get rid of the electrons, and the other one is going to be reduced. So sometimes between two metals, one will get oxidized and one will get reduced, right? Two dissimilar metals, you will have that happening. And that's what happens in our copper when we did the penny battery. Maybe a simple lab, but it has all of these concepts in there. Now, corrosion is huge. It does a lot of the things we do in our lives. Redox reactions are very important. They provide us with energy by transferring high energy electrons to low energy. Like I said, combustion reactions. Cellular respiration is a type of combustion. That's a redox reaction. Burning paper, combustion, photosynthesis, making salt, Haber process. We're going to talk a lot about this one in the future. All the ones over here, they tend to be reduced. All the ones over here, they tend to be oxidized. Metals tend to be oxidized. Non-metals tend to be reduced. Think of iron oxide, rust. That got iron is oxidized. By whom? By oxygen. So I like to look at that. If you do the opposite, if you get if you oxidize chlorine, you end up, if you have an ion of chlorine and you oxidize it, you take that electron, you make it go back to chlorine gas. You get back what you want. If you get a metal that is in the ion form, is combined with oxygen, and then you are able to give it back its electron, then you end up with your metal again. And don't worry about that part, we'll talk about that in more detail later. Oxidation loses electrons, becomes more positive, is a reducing agent, right? That's your metal. Metal. Reduction becomes more negative and is the oxidizing agent. That is your oxygen. Oxygen is your oxidizing agent. Think about oxygen when you're thinking about reduction. It's going to gain electrons, it's going to become more negative, and it's going to be, like the name says, an oxidizing agent. That's what I think about. I think of oxygen when I'm thinking about reduction, and I think of iron or any other metal when I'm thinking about what gets oxidized. The metal gets oxidized.
Can you leave it back on that side of it?
Yep.
Thank you.
So the metal gets oxidized, the non-metal gets reduced. And this is gonna have to go in because it takes a little while for those things to go in. Got it?
Thank you.
Oxidation numbers, we've talked about them before. Some things can vary their oxidation numbers, and you're gonna see how bad pretty soon. So these are the rules. The first rule, I don't think you need to write it down because you know it. What is the oxidation number of all the elements in the periodic table? Kate. Carbon, nitrogen, aluminum, what is their oxidation number before they combine, just as they are right now in the periodic table? They are like God made them. Excuse me? No, when they are like that, they are neutral, so they are zero. So if I have aluminum, as is written on the periodic table, same amount of electrons and protons, is neutral. That's the reason we have the same amount of electrons and protons, right? They're all neutral. All have a charge of zero. So that's what this is saying. Some elements are diatomic, still zero. Some have 8 atoms, right? Still zero. Any compound is zero, and that's what it's talking about in here. When you add up all the, like H3PO4, that's still zero. Compounds are stable, elements are not stable. So all of these ones are not stable, but their charge is zero, so that can be confusing. Now, these ones, their charge is also zero. Is also zero, but these are stable. That's when the electrons were transferred, when the electrons are shared, where something has done, the elements have done something, have combined to make compounds, because that makes them more stable, right? Questions on that? That's something we've seen before, right? Elements are not stable. Everything in the periodic table is like that, right? Not stable. When they combine and they make ions, they are stable. They attain noble gas configuration. There are 2 that will never, ever, ever change their oxidation numbers. Never. You're going to see today how some will. Alkali metals, no exceptions. They only have 1 little electron. They have to get rid of it, and then they have noble gas configuration. Believe me, they don't want to take an electron, period. Right? Alkali metals will always be +1. It's just 1 electron. Get rid of it, you are noble gas configuration. They'll never take an electron, no matter what happens. Yes?
So the elements that are all zero, that's everything but the alkaline earth, like the ones we're talking about?
No, they all have zero. This is when it's combined. These oxidation states happens when you are combined. You don't have oxidation states when you're by yourself, or when you're when you're combined, you do have it. That's when you get rid of your electron and you're assigned your -1 or +1. So when you are combined, alkali metals will always, always, always be +1. Alkali earth metals, I've always seen it be +2, but it's not one of the definite rules, so maybe there is one in which is something other than +2. Maybe it's a special case, I don't know. But I know for a fact these are always +1. Fluorine, the nasty one, always, 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 always -1. Fluorine, no exceptions. I don't care what you combine it with, I don't care if it's oxygens or whatever, fluorine is always -1. The other two that tend to be themselves 90% of the time, or maybe 95% of the time, are hydrogen and oxygen. Hydrogen, the only exception is obviously if it's combined with one of those, or it's in a peroxide. So if hydrogen is, well, I have peroxides with the oxygen, but no, hydrogens have only with alkali metals, hydrogens only with alkali metals, that would be their exception. That's the only exception. So if I have NaH, what is the charge of hydrogen? Marshall? In this compound, alkali metals have no exception, they're always gonna be plus. What would be the charge of hydrogen if they're in an alkali metal hydride?
1-.
Can you believe it? Hydrogen will be forced to be a minus. So that's an exception for hydrogen. Otherwise, hydrogen will always be plus, right? It's easy to get rid of that one, but if it's with an alkali metals have no exception. So in metal hydrides, alkali metal hydrides, it'll be minus, it won't be plus. Oxygen is always -2. Again, if it's an alkali metal, it will be whatever it has to be. 1:1 or 2:2 ratio, or peroxides. Peroxides is like H2O2. What is the charge of oxygen in H2O2 made? What is the charge of oxygen in H2O2? Yes. Right? Oxygen, you are like, what? Yeah, with peroxides. Hydrogen only has one exception. So oxygen will be -1. Oxygen has two exceptions. What if I have what is the charge, Zach, of oxygen in that compound? Oxygen difluoride.
+2.
Isn't that crazy? That's what fluorine does to you. Fluorine has no exceptions. It could make oxygen lose its electrons, so the oxygen doesn't want to do it, but guess what? Fluorine is not going to do it, period, right? So if you happen to have a compound like that, the oxygen will drop it, and this will be +2. That's crazy. I think it's crazy, but it is. Those are, halogens are normally -1, alkali metals are normally +2, but they can change. So let's do some examples to see that this is not as bad as it looks. This is talking about iron that's getting oxidized and reduced. This one. First thing you do is you look at the ones that were on that list. Your alkali metals, your oxygens, your fluorines, your hydrogens. You do those first, and then everything else falls in between. So potassium, what's the charge of potassium, Harrison? +1. And you have 2, so it's +2, right? What is the charge of your oxygen? always -2, right? Unless you're with an alkali metal or a fluorine or in a peroxide, right? So it'll be -2 times 7 minus 14.
Isn't that an alcohol metal?
But it's not right next to it. This is actually a polyatomic ion, right? So what will be the charge of chromium? The charge of the whole thing is 0. So +2 minus 14
Plus 12.
+12. So you have 2 chromiums. What's the charge of each chromium?
Plus 6.
Yep. Now, for people that find this difficult, there is a math, an algebraic way to do it. You multiply the atoms times the charges, so you have 2 potassiums times +1, plus you have 2 chromiums times x, plus you have 7 oxygens times -2, and all of that should equal to 0, and you can do it that way. Or you can just look and see. It's up to you what you want to do. But there is an algebraic way to do it. It's gotta be equal to 0. Does that make sense?
So when oxygen's with an alkali metal, it becomes -1.
Whatever it has to be, yeah. Or with fluorine, it is whatever it has to be to make the, because the alkali metal will never have an exception. What is the name of that polyatomic ion, Lauren? Yeah. And it came from what acid? If it's 8, it was ic, right? So it had to be carbonic acid. By the way, all our acids, except perchloric, are ics and they end in 8s. So it's phosphate, sulfate, carbonate, right? I don't know if we have another one, but I think that's it. It's all 8s and ics. We don't have the hypos. The hypos is when we start doing nonsense. So that's carbonate. And yes, some student in the last class said, hey, if I know that chromate is -2, can I do the same for getting the potassium? Yes. You could have gone O7 -2 is -14, and Cr2 will have to be the other. So that will be +12, because the total will be -2 for the polyatomic ion, right? So you don't have to do the whole thing as we did. You could just say, hey, forget that. This polyatomic ion is -2. You could do that as well, but it doesn't really save you that much. But that's what we're doing right now. We're doing the III. We're doing the carbonate. If we want to see the individual charges, so CO3, 2 minus. So the total thing should be -2. What do you do here, Lauren? Which one do you know for a fact?
I just knew that it was carbon, but you know that oxygen.
So that's -6. What's the charge of your carbon? Right? Because the total is -2, right? Now, Grace, MnO2. Just give me the charges. What the oxygen is -2, so Mn is what?
Well, it has to be +4.
Yes. PCl5, Anna. What's the charge of phosphorus? No. These are made up. These are charges that we are assigning. The only ones that are for sure are fluorine, oxygen, hydrogen, and alkali metals. So forget that.
-5, right?
Yes, they're 5 and it's -1.
And then,
Phosphorus will be what? The whole charge is 0. So it's important to do it because you are like, what? How can it be plus? It's supposed to be negative and it's on this column and what? Right? We do this to help us keep track of numbers, but yeah, it does, and that's a good thing that you went through that now because then you're like, oh shoot, you know? That's how it works. Now, SF4. Yeah, K202.
Me?
Yeah.
Oh. Potassium is plus 1. So, minus 1.
-1 for the oxygen, right? Which is weird. OF2, Ali. Fluorine has no exceptions, so it's -1. So all the fluorines is what? -2. What is the charge of oxygen? No, because the total charge is 0. So what's the charge of oxygen? 1 minus 2 is 0. 2. So it's a +2. Weird, right? Weird. And those are the hard ones because you're like, what? Oxygen being plus? Yep, that's what fluorine does to you. LiH. Okay.
Lithium is plus 1, hydrogen.
Uncomfortable, but that's what it is. You know, that's what it's telling you, right? So we're gonna do a worksheet next class that you practice a little bit more of this.
I have a question.
Yes.
So for PCl5, how did you know that you were going to use chlorine? Like, how did you know that?
Because in the worksheet, in the slide that we talked about, the order is you have to look at your alkali metals, you have to look at your fluorines, because those will make anybody else an exception, right? Then you look at your hydrogens, because they only have that exception. Next, you look at your oxygens, right? Because they have a couple of exceptions, but that's it. They're always what they are. Then halogens are usually -1, and alkali metals are usually +2. So if there is none of these are present, but you had a halogen, then the halogen will take precedence. Or the alkali earth metal will take precedence because they're usually -1 and they're usually +2. I've never seen this one be anything other than +2, but I know it's not written like that in any rules. So maybe there is one that I don't know out there, probably. So, a little bit more practice so that you get a little bit more comfortable with this. Yes?
So, like, if we have, like, a equation, how would we write it? Like,
We're gonna do that when we do the lab. But what is the oxidation number for this? Were we going forward? Yeah. Marsha, what's the oxidation number for that? 14.
Fast is +1 and is
No, hombre, that's the same composting.
0.
Yeah. What? 0. What's the oxidation number for Anne Bradley for nitrogen? 0. Because it's like God made them, right? They're not stable, but what's the oxidation number for chlorine? Yeah, that gave it to you, right? You say +2, that'd be an issue. What is the oxidation number for calcium? They give it to you, right?
Miss Thompson, would you know whether to +2 or 2+?
It's supposed to be 2+. It's supposed to be. But guess what? People just go back and forth
It
all
doesn't
the
really
time.
matter.
No, nobody will ever penalize you for that. Some cranky teacher will say, well, I want to see it always like this because this is the way it's supposed to be. But everybody, because you're adding them, so to add them, you really want to do +2, -1, right? So, yeah, like I didn't make this PowerPoint. It was originally made by a friend. And I'm like, Now, LIF, where Where were we? U, LIF.
Feel would be +1 and fluorine would be -1.
Yep. H2S. Anna.
Oxygen will be +2. Right?
Mm-hmm.
No, yeah, +2 and then sulfur would be -2.
Yeah. MgO.
Would it just be +2?
Yeah, that's an easy one because that's nothing special. That one actually follows all the rules. Now, what about this one, Harrison?
Cesium's +1, oxygen's -1.
Yep. Because it's in a 1-to-1 or 2-to-2 ratio with an alkali metal. And alkali metals will never be anything other than a +1, right? pH3, Ali. So hydrogen is +1, so it is +3. And the phosphorus will be what? Yep. Oh, let's do these ones. K. Sodium bromate.
Na is +1.
Mm-hmm.
And bromine is -2.
Yes. The one that doesn't is oxygen.
Okay, so oxygen has a -6. So then bromine has to be +1.
Yeah. See, it's not too bad. And you could have said, hey, that's a bromate, so that's +1, that's -1, and do it from there, right? It would have been the same answer. Magnesium sulfate made. So the sulfate is -2. And what is the sulfur and the oxygen? Yeah. Yeah. Because the whole thing is -2. Most people have been telling me +8, but you know, you gotta think about the charge of your ions. Zach, lithium nitrate. I wanna know the charge of nitrogen. You can tell
E
him?
-1.
No.
Oh.
She gave you the wrong thing. Don't trust her 100%. Sometimes she's just kidding.
So,
Nitrate is -1. So you could have that nitrate, but I want nitrogen.
Nitrogen's +1.
Yeah? Because that's -6 + 5, right? It's like, why did you do this to me? Because she wants to make sure that you trust yourself. That's what she wants to do. Now let's go and do this experiment so that I wake everybody up. Although you are not falling asleep today, except you.
Cut the camera.
What?
Cut the camera.
Well, let me do it for the kid because she's not gonna do it. So we'll do
Okay.
this real quick.
Yeah.
Do one and then you got it.
What is this?
Oh wow.
what is
Right?
that lighter?
That's just a lighter. The important part is the paper.
Wait, I wanna do it. That was fun.
Yeah, wait, do we all get to do that?
So yeah, so what I wanted to tell you is what's happening here. If I burn paper, I'm running out of fuel, but if I burn paper, I told you that most things that you burn that has carbon, hydrogen, and oxygen, and this has cellulose, which has carbon, hydrogen, and oxygen. CHO plus O2, what does it make? CO2 plus H2O. But it didn't. It made all these little things that fell out and all that. Why? Incomplete combustion. Only 20% of the air I have in here has oxygen. So a lot of that doesn't just burn all the way because it doesn't have enough oxygen. What they do to this paper is they treat it. And now it has a whole bunch of oxygen in it, right? So they treat it and it has a lot of oxygen. So when you burn it, it burns completely. And then you don't have to worry about having any extras. Do you know who used to use this paper for real? And it was illegal to sell this paper until magicians and chemistry teachers got a hold of it.
Is that tissue paper?
No,
Like
it's regular paper, but it was treated to add oxygen to it, to add some nitrates in there.
Does
And
it feel like tissues?
they were regular paper.
Looks like
What's it feel like?
Oh, you're gonna feel it in a minute. It just feels like paper that was treated.
What is that?
It feels almost like a tissue. I never thought about what it felt like. It's just paper. They also do this with cotton. I don't like cotton. I prefer paper because I'm farther away from the flame.
Wait, you never told us why it was illegal.
Oh, because drug dealers used to. Because they used to write a lot of their important information in this paper, so when they had a raid,
Invisible.
no, they'll just burn it and there will be nothing left, right? Yeah, well, sometimes we're not thinking when we talk. But yeah, but it used to be drug dealers and people like that used to write how many people they killed and all that nonsense. And all whatever else they had. Who were their hit people? I don't know what they wrote, but they wrote something in there. And
Want me to stop videoing, Thompson?
yeah.